almost all the questions except the pipeline ones. And the pipeline question is very like crossing the river question, so they kind of take the same thing. So this is a version of question 17. So I'm just reading it out and kind of building it as we're doing it. An oil refinery is located on the north bank of a straight river that is 1 kilometer wide. Here we go. And up here, we have the oil refinery. So I'll call that R for refinery. And I know that from here to here is 1 kilometer. So that's that piece of information done. A pipeline is to be constructed from the oil refinery to storage tanks on the south bank. That's going to be some storage tanks over here. And it's 10 kilometers east. So the distance from, well, I guess I should say, the distance from here to here is 10 kilometers. Okay. Now, the cost of laying a pipe over land is $500,000 a kilometre. And if you do it under the river, it's going to cost you 1 million. And we are being asked to minimise cost. There are 3 possible solutions to this puzzle. Solution number 1 could be that you just go with a pipeline straight to the storage tanks. So you don't go on land, it's straight under the water. So I'll call that RS. And we'll find the cost of it. The second way of doing it was R to this point here, directly south of it, I'll call it E. And then from T to S. So there's going to be pipe RT plus a TS. And then the third possibility would be that maybe not, but maybe there's some point here. I'm not sure it was but RSTUVW, like W for no particular reason. And you go from R to W, and then you go from W to S. Now, this question 17 is exactly the same as 18. All they do in 18 is change the cost of things. So to remind you what the cost on this story is, if the pipe is under the water, if it's in the river, it's going to cost you $1 million. If it's on land, it's going to cost you $500,000. So what I'm going to do here is we're going to look at each one of these options and find out what it would cost, right? And whatever one of those 3 is the minimum, that's the answer we're looking for. Now, the first 2 don't involve calculus. So let's do the first one, R to S. Now, if I simplify the piece of information that we're interested in, is there's R, there's S, this is 1, this is 10 kilometers. Would you agree that all I need to know is how long that pipe from R to S is? Would you also agree that's not calculus? Would you agree that's just Pythagoras and it's the square root of 101? And don't we also know that when it's in the river, which this is entirely in the river, the cost is $1 million a kilometer. So whatever that number is times 1 million. So the cost of going from R to S is the square root of 101 times 1 million. And I'll round that off to some convenient number. square root of 101. It's that guy, times 1,000,000. And the answer is 1,004,000. I got that right? Not 1,000,000. Try that again. 10,049,875. Okay, so didn't need calculus for that one, right? Now the second option was you went straight down the way, that distance in water, and then straight across. So we're talking about RT and then TS. RT is a kilometre. That's 1 kilometre times the cost, which is 1,000,000. And TS is 10 kilometres. And 10 kilometres times 500,000. And that one ends up being 1,000,000 plus 5,000,000 ends up being 6,000,000. So would you agree that it's not a good idea to build the river one? It's far too expensive. This one is better, right? You still have to use some of the river. It's going to cost you 1,000,000 going that way, plus another 5 going that way. So your total cost is now 6,000,000. And now the one that needs calculus, the third possibility. Since I'm running short of space here, I'll just put the price up here. 10,049,875. This one here is what, 6,000,000. Let's figure out what the cost of RWWS is. I'm just going to draw another version of that picture so I can write some stuff on it. Here's R. There's T. And here's this guy called W. I know that this is 1 kilometre. But I don't know the distance from T to W. In fact, that's going to be the guy I'm going to find. So I'm going to call him X. What is the distance RW going to be? Well, if you imagine that that's a little right angle triangle, won't RW be use Pythagoras? And won't the distance from R to W be 1 squared plus X squared?
Mr. Robertson, there's someone trying to get in. A student's computer crashed.
Thank you. It's Mia. Gotcha. Are we okay with the distance RW being this square root of 1 plus X squared? Are you comfortable where I got that? I just called this guy X because I don't know what it is, right? And 1 by X, right angle triangle, we got that guy. Now, if we move a little bit further down the coastline, we get to the storage tank. Now, I know the total distance from here to here is 10. But what's the distance from W to S? And again, it has to be in X's.
10 minus X.
Are we comfortable with how we got that? That makes sense. So now let's get the cost. The cost of this pipeline is made up of the RW part plus the WS part. The RW is this fella, and it's in the river. And when you're in the river, it's $1 million a kilometre. So what you're going to do is you're going to take this guy, the distance, times 1,000,000. Now this distance, WS, that's 10 take away X. And when you build on land, it's going to cost you 500,000. So you've got that. So I'm going to call this function C of X. The cost function is 1,000,000 square square root of 1 plus x squared plus 500,000 times that. And 500,000 times that. That is one really, really ugly function, isn't it? It's basically a multiple of this, 5 million, you know, we multiply it by 10, take away this guy. So far, so good. Now, whenever we have an optimization function, shouldn't we find its derivative and then critical numbers? So its derivative is basically, I'm going to call that 1 plus x squared to the half. And if I do that, you're just going to have to trust me. But you can check it later. This is the answer that you get. Probably take you about 2 or 3 lines, but that's what you'll get. The derivative of this guy is not a problem, right? Because that's 0. And the derivative of this guy is just a very big number. Now, what we should do is find critical numbers, which is we should find out when this function, this derivative function, is 0 or when it's undefined. I'm not too worried about undefined because there's never going to be a problem with that being 0. So I'm only going to focus on that. Now, I guess I could try and solve that algebraically. Would you agree that it ain't going to happen? I can't really solve it algebraically. So what I'm going to do instead is put it into Desmos and let it find out. So I'm trying to find out when this is 0. Because whatever value of x makes this 0, that's going to be the magic number for here. And that's where you should build your pipeline. And we'll check its cost. And if it's smaller than the 6 million, that's the one I'm going to use. So right now, I'm nipping over and setting up Desmos. And fingers crossed. You are looking at Desmos, yes?
Yes. Yes.
Great. So, oops, I'm going to go over here and play about with Desmos. It is such an ugly function. It might be a challenge, but we're going to get it. I'm just going to call it y equals because it's less hassle. It's 1,000,000x divided by the square root of, I guess I'll need this little guy. There we are. You can see it for a second. 1 plus x squared. And take away 500,000. Oh, it isn't. What is it? Yeah, it is 500,000. 1, 2. Okay.
So
Do
instead
you
of
notice
zooming
that
out,
it's not much of
instead of zooming out, you can
Say again,
press
Robin?
the wrench there and set it to parameters.
Sure. I'm going to be lazy and say, I don't really need to know how curved it is and what it does because isn't the place I'm looking for where it crosses x-axis? And can you see that it's at 0.577? When is this function 0? It's 0 when it crosses the x-axis. Where does it cross the x-axis? We're at pointing right now. So we have found that x is equal to 0.577. So let me go back and take that answer now. So I'm not even trying to draw the graph. I'm only trying to find when it's 0. And we got that. It's this number. So I guess the question is, if you make this, it's about 0.6 of a mile. If you make this distance here about 0.6 of a mile east, according to what we've got, that might well be the cheapest route. So I now have to find the cost when X is this number. And it ends up being $1,000,000, 1 plus 0.577 squared plus 5 million take away 500,000 times 0.577. Since I don't want to spend really any more time, I will go and tell you the answer. By just getting WebAssign to tell me it. And according to WebAssign, oh, shoot, space. Doesn't want to tell me. Okay. Try asking for a solution. Oh, here we go. No, sorry. I can't tell you what that is because it won't tell me. Oh, darn it in space. Okay, I'm going to do it. I just didn't want to do that calculation. So anyway, is there any way I can make my life easier? I could do it in terms of millions. That'll make the calculation a little bit quicker. So it's 1,000,000. So it's 1 times 1 plus 0.577 squared plus 5 million. Oh, this isn't too bad. Take away 500,000 times 0.577. And the answer I get is 5.6 million. So 5,866,000 and 25. And that is cheaper than 6 million. So you can save about 100 odd thousand by doing that route. Does that make sense? It's a really ugly calculation, but you know, I can live with it now. What this is showing is the power of calculus. Before calculus was invented, if calculus wasn't invented, we wouldn't even be building pipelines, to be honest. I mean, I'm not even sure you could build a bridge without calculus. I mean, you could kind of build it and hope it didn't fall down, but if you don't have the math that's behind the engineering, you wouldn't be able to do any of those things. But it does allow us now to optimize things. And I think that's kind of cool. So what do I want to talk about now? Well, a couple of things. First, your test. And secondly, I want to talk about how you can calculate what you need to get in the final, very roughly, to pass, to get 4.0 and so on. But first things first. Test 5 is coming up, as you all know, and it will be, oh, darn it in space. There we go. I'm just trying to get the right window open here and failing miserably. Right, I'll move this over and we can look at the topics that test 5 will have. So, first, you may not be doing test 5, some of you. Since I count the best 4 out of 5, if you've got really good 4 tests, you might want to spend that time getting ready for your final and just not take it, and it won't have any effect. If you've missed a test or done badly, you really should do it. If you want practice, do it as well. But you might think, well, suppose I end up practicing and I do really badly in it. It doesn't matter because I only count the best 4, in which case your grade will stay the way it is. So you can't lose out of it. So it's up to you what you want to do. Here are the topics. We are going to have 4 questions. Does anybody know which one of those 5 topics is not going to be tested? Because I have mentioned it.
Shapes of graphs, I think.
Yeah, so number 5, curve sketching.
Oh.
So I think that's what I hope. Not
Yeah.
4-3, but that
But
you
4,
might have
I confused.
described it. Sounded like it was 4-5.
Yeah.
We're not going to be sketching, right? They take far too long. Anyway, the stuff you need to sketch them is in the other 4 anyway, so it's not like you don't get tested. So you're going to get 1 question from each of these 4. And where am I going with the rest of my brain here? We need to look at how to calculate your grade now. And I have some tidying up to do, I've just realised. On antiderivatives as well, but that's fine. Okay. Where the heck are you? You were sent out a letter, and you'll get another letter on Monday, well, maybe Tuesday, to be honest, which will tell you what your grade is. But let's just say that your grade is 80%. And what I'm going to show you is what you need to get in your final to pass and so on. So what you're going to do is you're going to find 80% or whatever your percentage is of 700 points. And that gets you 560 points. And that I'm calling your raw score. So far, so good? Now, get a 2.0. Get 3.0. And then to get 4.0. To get a 2.0, you need to have a total score, right? That's including the final of 750 points. To get a 3.0, you need 850. To get a 4.0, you need 950. So all you do is you take that raw score, subtract it from this number, and that will be, what will that be? It'll be 190. So if this was you, you need to get 190 out of 300 points. So about 63%. You could fail, but it's a pretty comfortable place to be, right? You only need to get 63%. Now, if you wanted to get a 3.0, you need, this person will need 290 points out of 300. I've seen people get 300 out of 300 in finals, but it's very rare. But, you know, maybe you'll have a great day and that's you. And this person ain't getting a 4.0. Just no matter what they do, they couldn't do well enough in the final. Even if they got a perfect, it still wouldn't do it. Now, every 10 points is 0.1 on this. So for instance, if you get 200 points in the final, it'd be a 2.1. Right? If you get 210, it'd be a 2.2 and so on. So there's your kind of, that's your magic number for passing, and then whatever your particular situation is for the rest. Are we comfortable with that? Okay, let's do some more tidying up then.
It seems like we should be able to use a calculus formula for a minimum or a maximum or something on that.
I think it would just be a linear function. I've not tried it, but I think it would be. Right, so let's do antiderivatives of trig functions. Let's do double antiderivatives, and hopefully to finish with velocity acceleration. Right, I'll stick a 3 in front of it. You just have to be able to memorize it. What function would you need to start with that if you differentiated it, you get 3 sin x? God, that's a kind of back to front thing, but what would you need? What's the antiderivative of sin x, essentially?
Would it be -3 cosine, or would it just be 3 negative cosine?
Well, I think if you put them together, they end up being the same thing.
Flat.
Correct. So if you find the antiderivative of a sine, you get a negative cosine. What is the antiderivative then of a cosine?
It'd be 5 sine for this one. 5 sine plus.
Yeah. Yeah, plus a c. Have you noticed that the antiderivatives are the opposite of what derivatives do? If you differentiate a sine, don't you get a positive cosine? But if you find the antiderivative of a sine, you get a negative cosine. Have you noticed that's back to front? What happens in the future is, because you will be differentiating and in some questions also finding antiderivatives, that you'll start merging those two and you won't remember if it's a plus or if it's a minus. But you've got to somehow figure out what that is. This one is because you've got a good memory. What function is the antiderivative of secant squared?
Tangent.
Tangent. Have you noticed that when you talk about antiderivatives of any of the trig functions, isn't it really mostly memorized things? I just have to remember that the antiderivative of secant squared is tan. There's not really a formula or something that allows you to do it. How about this is the last one? What is the antiderivative of a secant tan?
Secant.
It is in fact secant. Don't forget your plus C's. Okay, so that's that little tidy up. Are we good with that? It's really just memorize them. I mean, there's no trick to it. Just memorize the damn things. Right. How about this fella? I'm going to have to change notation here, and that's fine. Normally, the notation is like this. And you're asked to find the antiderivative. And you add 1 to the power and you divide by the new power, right? And you get that. That's what we were doing yesterday, agreed? There is another notation, which for some people is much more natural. And that is, I will tell you the derivative is this guy, and I will ask you to find him. You see that although that looks different, isn't that the same exact question?
Excuse me, I
It's
think,
just the way they phrased it. Yes.
did you forget on the antiderivative, it should be 1/3 x to the 3?
Oh, well, no, I divided by 3, and 3 divided by 3 gets you 1.
Oh, yeah, thanks.
Right. There is a 3 there, but it cancelled out because there was a 3x squared. Right. We're good with this, right? So you could be given a question where it says, this is f dash to find f of x, or it could be phrased, this is f of x, find the antiderivative called f of x. It's the same process. Now, why is this notation useful? Well, you can get a question that looks like this. Suppose I tell you what the second derivative is, and I ask you to tell me what the original f of x is. You see that the way you're going to do that is you're going to have to use antiderivatives twice. The first time you do an antiderivative, won't you be finding the derivative function, right? But if the second derivative is this, and I find the antiderivative of it, aren't I basically undoing one of the derivatives? Now, add 1 to the power, divide by the new power. Add 1 to the power, divide the new power. And what's the antiderivative of 2e to the x? Yes. Correct, is he? Yeah. Oh, I almost forgot my plus c, didn't I?
Didn't know you were
Don't
well
forget
versed
your
in sign
pluses.
language.
No, I just actually figured out that the hand movements looked like e to the x or whatever, so I just did it from there. Now, if I work backwards, in other words, if I find the antiderivative of this, won't I get the question? Right, I'll get the original function. Now, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. That guy. Now, what does this plus c get me? What's the antiderivative of plus c? Not just c, no. If it was 5, wouldn't you get 5x? If it was 10, wouldn't its antiderivative be 10x? So since it's c, you're going to get cx plus, you do not write plus c. You pick a different letter of the alphabet. Why am I calling it this second time? Why am I calling the arbitrary constant d and not cx plus c? There is a reason for that. Why is it not cx plus c? Why is it cx plus a totally different guy, d?
Because you could be confused as a same number, the exact same thing.
Yeah, and we know that there's no reason for that. Couldn't the c be 5 and the d be 20? If you make the same letter in math, you're saying the same, they're both the same number. And we know that when you do antiderivatives, the arbitrary constant could be any number. And if you do it again, it could be a totally different number the next time. So that's that guy. Are we comfortable about how if you're given a second derivative, you could work backwards twice or 3 times? Here's a really good one. I'm not going to do it. Well, I won't do the individual stages. But if I told you the 6th derivative was this guy, could you have a guess at working back 6 times to get the original function? Have fun with that one. I won't do it. Right. So now we're going to look at an application. Suppose I tell you the velocity of a function is 4t squared plus 6t plus 2. and I tell you that the position of the object at time 0 is 5. I can find the formula for the position of this object, right? Its position function. And we typically call the position function s of t. Isn't the velocity a derivative function? So if I find the antiderivative of velocity, won't I actually be finding the position function? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. 2 gets you 2t plus c. What do you think that piece of information is going to help us find?
C.
Yeah. And how do you right, I'm not sure. Hold on a second, people. God, I'm annoyed at this machine sometimes. It's a real pain in the butt. Right. It said that I just shared, I'd made somebody the host. If I accidentally made one of you the host, will you unhost yourself so we can keep the video going? Because I lost half a class yesterday because somehow it switched over to someone else. So anyway, we've decided that you can use this information to get C. And my question is, well, how do you use this information to get C? What do you do? Can I find S of 0 then? And S of 0 is 4/3 times 0 cubed, 3 times 0 squared, and 2 times 0 plus C. And that is equal to 5. And since they're all 0, doesn't that make C 5? So we now know the position function. It's 4/3 this guy, 3 of those guys, 2 of those guys. Missing. Oh, not a C. 5 now, because we know C is 5. Right, last question. Suppose I have an object whose acceleration is changing, right? Its acceleration is 4t plus 1, right? So when t is 3, the acceleration would be 13 meters per second squared. Suppose I tell you that the velocity at 0 is 2, and that the position at 0 is 10. Knowing the acceleration and these two pieces of information, which are sometimes called the boundary condition, I can find where that object is in space. All I know is its acceleration, its velocity at time 0, and its position at time 0. But evidently, according to calculus, I can create a formula for where that object is, its position at any time. So let's see how that works. Right. What do you get if you find the antiderivative of acceleration? What are you finding?
Velocity.
So the antiderivative then is 2t squared plus t add c. I'm now going to use this piece of information. Can I speed things up and say that it ends up being 2? Right? If you plug that in and solve it, c is 2. Now, what do you get if you find the antiderivative of velocity?
The position.
Okay. And the position at time t is 2/3 t cubed half t squared plus 2t plus c or d or any letter of the alphabet you want. And then I use this thing to find c, and you can just trust me that it ends up being 10. What that tells me is that if you have a moving object and all you know is how its acceleration is changing through time, and a couple of other things, you know everything you ever wanted to know about this object. Don't you know its velocity at any given time? Don't you know its position at any given time? Isn't that basically everything you could possibly want to know about this object? Now, before calculus was invented, that was just an impossible task. No one would be able to figure out how to do that.